So in question number 3, we have a single phosphorus 32 nucleus can be produced when a single sulfur 32 nucleus joins with particle X. In the process, a proton is emitted. What is particle X? So let's write down an equation for this. What we have is sulfur 32. When sulfur 32 combines with particle X, it produces phosphorus 32 and a proton is also emitted. So this is the equation that we have here, and since we're talking about the nucleus, we need to look at subatomic particles in the nucleus. So over here, sulfur 32, sulfur is atomic number 16, so that means it has 16 protons. It has 16 protons, and because the nucleon number or the mass number is 32, the number of neutrons is simply 32 minus 16, so we have 16 neutrons. Now we don't know what particle X is, but we do know that in the products we have phosphorus 32, which has 15 protons, because that's the atomic number for phosphorus. And we have 32 minus 15, 17 neutrons. And obviously we have this proton emitted over here. So now if you look at the left-hand side and the right-hand side, on the left-hand side we have 16 protons, and on the right-hand side we have 15 plus 1, 16 protons. But here on the left we have 16 neutrons, whereas on the right we have 17 neutrons. So that means that we have one fewer neutron on the left-hand side. So particle X must be a neutron. Particle X must be a neutron. So here the answer is C, that particle X is a neutron. The next question that we have here is question number 19. Now question number 19 says, sulfur dioxide SO2 reacts with calcium hydroxide in aqueous solution. What is the main product that is first formed? So we know that sulfur dioxide is an acidic gas, and we know that in water, sulfur dioxide forms sulfurous acid, or the ion that sulfur dioxide forms is sulfite ion. So what we have here is H2O, resulting in the formation of H2SO3. And here we have sulfite ions. These are formed from sulfur dioxide in aqueous solution. So when calcium hydroxide reacts with sulfurous acid, calcium hydroxide is a base that's reacting with sulfurous acid. So this is a neutralization reaction resulting in the formation of calcium sulfite, which is CaSO3, plus 2H2O. So our product over here that's formed is calcium sulfite, which is CaSO3. So the answer here is C, CaSO3. The next question that we have here is question number 20. Now question number 20 says, structural and stereoisomerism should be considered when answering this question. Compounds X, Y, and Z are shown. How many other isomers are there of 3C3H7ClO that are alcohols? Now they've already given us 3 isomers. They want to know how many more isomers are there with this molecular formula. Now if you notice the options that they've given us, X and Y, the OH and the Cl groups are on the first carbon, and they're optical isomers of each other. So when the OH and the Cl are on carbon number 1, what we have is 4 different groups on carbon number 1. So we have a pair of optical isomers. And in Z, we have a 3-carbon chain. We have a 3-carbon chain where the Cl and the OH are on the middle carbon, carbon number 2. So they've covered the possibilities where OH and Cl are on the same carbon. So now let's see. Now if we have a 3-carbon compound with this molecular formula, we know we can't have a branched chain with these 3 carbons. So we must have a straight chain. And let's consider the part when I have the OH on carbon number 1. Now they've already given us the chlorine on the same carbon. What if the chlorine was on carbon number 2? What if the chlorine was on carbon number 2 over here? What we have is CH2OH over here. We have a CHCl and then a CH3. And if you notice, this carbon here is a chiral center. It's bonded to a chlorine, a CH3, an H, and a CH2OH. So it's bonded to 4 different atoms or groups of atoms. So we can say that this is a chiral center. That means for this particular structural isomer, we'll have 2 optical isomers. So it'll exist as a pair of optical isomers. So we have 2 different possibilities with the same structural formula. Now, we can also have an OH on the first carbon, but now instead of the chlorine being on the second carbon, the chlorine is on the third carbon. There we end up with CH2Cl on one end and a CH2OH on the other, and we have a CH2 in the middle. This particular structural isomer does not exist as a pair of optical isomers. If you notice, each of the carbon atoms is bonded to two identical hydrogen atoms. So therefore, there's only one possibility for this structural isomer. And the last possibility that we have is that instead of the OH group being on the first carbon, what if the OH group was on the middle carbon? What if the OH group was on the middle carbon? Well, now we can have a chlorine on this guy or this guy. It doesn't matter. It'll be carbon number 1. It could be this or this. They're identical. So let's just take this carbon over here, Cl. Now what we have is CH2Cl. We have a CHOH and we have a CH3. Now again, if you look at the central carbon here, it's bonded to an OH, an H, a CH3, and a CH2Cl. So again, what we have here is a chiral center. So this particular structure exists as a pair of optical isomers. So we have two different possibilities for this. So the total number of isomers that we have in addition to these three is 2 plus 1 plus 2, which is 5. So the answer here, there are 5 other isomers of C3H7ClO that are alcohols. Next we have question number 31. Question number 31 says, nitrogen forms a number of oxides. Their enthalpies of formation are given. Which statements are correct? If N2O is oxidized by oxygen to NO2, 16 kilojoules is released per mole of N2O. So let's examine statement 1. So statement 1 says that if I have 1 mole of N2O and I oxidize this to form NO2, the enthalpy change should be negative 16 kilojoules per mole of N2O used. So let's balance this equation, making sure that we have 1 mole of N2O here. So that means we're going to have 2 moles of NO2 because we have 2 nitrogens on the left. And if we have 4 oxygens, we can simply balance this by saying 3/2 oxygen. So this is our balanced equation. Now the enthalpy change for this reaction, we can use Hess's, we can draw a Hess cycle, but we know that if we've been given formation enthalpies, we know that the delta H for a reaction, is simply the delta H formation of products minus the delta H formation of reactants. And here what we have is, we have our products, which is NO2, and we have 2 moles of that. So 2 moles of NO2 means 2 times 33 over here, 2 times 33 minus the formation of the reactant, which is N2O, and that has an enthalpy change of plus 82. So 2 times 33 minus 82. And this gives us an enthalpy change of minus 16 kilojoules per mole. Since it's negative, it means that 16 kilojoules are released per mole of N2O oxidized. So that statement is correct. So statement 1 is correct. Statement 2 says the decomposition of N2O to N2 and O2 is exothermic. So if you look at statement 2 here, if I take N2O and I decompose it into its elements, we have N2 plus half O2. Well, if we notice, this is simply this is N2O decomposing into its element. So the reverse reaction here is the formation of N2O. From its elements, we form N2O. So delta H formation of N2O we already know is plus 82 kilojoules per mole. Plus 82 kilojoules per mole. So that means the backward reaction has the same magnitude, but instead of being endothermic, it would be exothermic. So we know that the backward reaction must be minus 82, which is the decomposition of N2O into its elements. If formation is plus 82 from elements to product, then product to elements must be minus 82, which is again exothermic. So the answer, so part 2 is also correct. The last question says the reaction between nitrogen and oxygen, or nitrogen monoxide and oxygen, is exothermic. When nitrogen monoxide reacts with oxygen, this is statement 3. When nitrogen monoxide reacts with oxygen, what we have is the formation of nitrogen dioxide. Now the enthalpy change for this reaction will be again products minus reactants. So the formation of products over here is, well, nitrogen dioxide is being formed, 1 mole of nitrogen dioxide. So that over here is plus 33 minus the delta H formation of reactants. the formation of nitrogen monoxide is plus 90. So 33 minus 90. And that gives us an enthalpy change of minus 57 kilojoules per mole of nitrogen monoxide or nitrogen dioxide formed. So the idea here is, again, this is an exothermic reaction. So statement 3 is also correct. So all 3 statements are correct, hence the answer must be A. One more thing to note over here in statement 2 is that we can use the same idea here as we used in statements 1 and 3, which is that formation of products minus reactants can give you this enthalpy change. Now, since we have elements in the products, the formation for them is 0 minus the formation of N2O. So negative formation of N2O is simply negative 82. So we can use the same idea in part 2 as well. The last question that we have here is question number 32. Question number 32 asks, which statements are correct? The enthalpy of combustion of hydrogen is equal to the enthalpy of formation of water. Now, the enthalpy of combustion of hydrogen refers to 1 mole of hydrogen gas, because it's in a standard state, being completely combusted in excess oxygen to form 1 mole of water. And all the reactants and products are in their standard state. Now, if we notice, the formation of 1 mole of water, which is the enthalpy of formation of water from its elements in their standard states, the formation of 1 mole of water from its constituent elements requires the combustion of 1 mole of hydrogen gas in excess oxygen. The complete combustion of 1 mole of hydrogen gas results in the formation of 1 mole of water. Hence, enthalpy of combustion of hydrogen is equal to the enthalpy of formation of water. So statement 1 over here is correct. Now, statement 2 says the enthalpy of formation of hydrogen is equal to the negative enthalpy of atomization of hydrogen. Now, formation of hydrogen is simply 0 because the formation of an element is considered to be 0, is equal to 0. Whereas the negative enthalpy of atomization of hydrogen is, well, we know that atomization refers to the formation of 1 mole of gaseous atoms. So we're forming 1 mole of gaseous hydrogen atoms, which means half a mole of hydrogen molecules are forming 1 mole of gaseous atoms. That's the enthalpy of atomization. Now, this is simply us breaking half a mole of covalent bonds between 2 hydrogen atoms. This is half a mole of hydrogen-hydrogen covalent bonds being broken to form 1 mole of gaseous atoms. And we know the bond enthalpy is 436. So this is the enthalpy change of atomization, which is 218. So negative atomization is when we go from 1 mole of gaseous atoms. We go from 1 mole of gaseous atoms to form half a mole of hydrogen gaseous molecule. So this is simply negative half times 436, which is negative 218 kilojoules per mole. This is not equal to 0. So therefore, these two enthalpy changes are not the same. So we can say that statement 2 is incorrect. So if we know that 1 is correct and 2 is incorrect, we know the answer is D. Let's examine statement 3. Statement 3 says enthalpy of solution of HCl, which is when we dissolve 1 mole of HCl, a covalent molecule, we dissolve 1 mole of HCl in sufficient water to form an infinitely dilute solution, is equal to the enthalpy of hydration of H++ enthalpy of hydration of Cl-. Now, enthalpy of hydration refers to dissolving 1 mole of gaseous ions to form an infinitely dilute solution in sufficient water. So here we have 1 mole of a covalent molecule dissolving in sufficient water, whereas over here we have gaseous ions dissolving. So these two enthalpy changes are not the same. So therefore only one is correct. So the answer is D.